Okay, I understand the instructions. Here's the translated and rewritten version of the text, aiming for a clarified and slightly expanded style, but remaining faithful to the original content and tone. The rains in Wisconsin's dairy country possessed a unique character. Samuel Hartwell discovered this during his inaugural summer in 1882, when a mere 8 years after construction, his barn's sill log exhibited black rot. This mirrored the experience of every dairy farmer across the upper Midwest, who were routinely advised that sill logs should be tightly fitted against stone foundations for swift and enduring stability. By the 10th year, Samuel was facing a $200 repair bill, and the same insidious rot was spreading through barns built using standard methods across 3 counties. His subsequent idea was initially dismissed by his neighbors as foolish, introducing a gap between the foundation and the wood, a concept that flew in the face of accepted building practices. Yet, 35 years later, Samuel's sills remained pristine, while conventionally built barns were falling apart. We'll delve into the precise steps behind this deceptively simple modification. What understanding of moisture did he possess that eluded every other Wisconsin builder? The Wisconsin Territory had been imparting the same lesson to barn builders since the 1840s. Stone foundations signified permanence. Every carpentry manual, from Chicago to Milwaukee, championed the principle of direct contact between sill log and foundation stone. The rationale appeared indisputable to those who worked with their hands. Stone, it was believed, did not transmit moisture because it remained dry above ground. Wood placed directly on stone maximized the bearing surface, effectively distributing the barn's immense weight. Crucially, this method demanded no intricate joinery, specialized hardware, or materials beyond what any dairy farmer could readily obtain locally. Samuel Hartwell had absorbed this conventional wisdom through 15 years of observing barns being erected across Dane County. His father had constructed their family barn in 1867 using the standard method, and it had successfully supported the weight of 40 dairy cows, 3 seasons' worth of hay, and countless Wisconsin winters. When Samuel married and acquired his own 160 acres in 1879, he naturally adhered to the same blueprint that had served his neighbors for decades. The construction process followed time-honored steps that any trio of farmers could accomplish in a single weekend. First, they established a foundation of quarried limestone blocks, each stone approximately 18 inches square and 8 inches thick, mortared with lime and sand to form a level rectangle. Next, they selected the finest available oak logs, typically 12 inches in diameter, and hand-hewed them flat on the top and bottom to create tightly fitting sills. These sills rested directly on the stone foundation, with each joint meticulously scribed and cut to eliminate any gaps. Iron drift pins, driven through the sills and into the stone, secured everything in place. This method yielded barns that stood square and solid from the moment the roof was installed. However, Samuel began questioning this accepted practice during his 3rd year of farming, not because of any dramatic failure, but through careful observation of details that other farmers disregarded. He noticed dark staining where his sills met the foundation stones, despite both materials appearing completely dry to the touch. He observed similar staining on every barn he examined closely, ranging from the newest constructions to structures built 2 decades prior. Most significantly, he discovered that this staining appeared irrespective of how well the barn had been maintained or how meticulously the foundation had been constructed. The breakthrough in Samuel's thinking originated from an unexpected source, his experience repairing stone walls on his property boundaries. While rebuilding a collapsed section of fieldstone wall, he noticed that stones resting directly on the soil remained noticeably damper than those elevated, even by a few inches above ground level. The soil contact stones exhibited moss growth and mineral staining that the elevated stones never developed, even when both were exposed to identical weather conditions. This observation compelled Samuel to reconsider his established understanding of moisture transfer between stone and wood. Traditional building wisdom held that capillary action ceased at the stone surface. However, Samuel's fieldstone experience suggested otherwise. He began to suspect that moisture could travel from the soil, through the stone and into the wood via mechanisms that standard construction practices completely overlooked. The implications troubled him, suggesting that every barn in Wisconsin might be gradually failing due to a process that builders considered impossible. Samuel's growing concerns were validated through conversations with John Brennan, a German carpenter who had immigrated to the area in 1871. Brennan shared techniques from his homeland that Samuel had never encountered in American construction. German builders, Brennan explained, often elevated their seal timbers above stone foundations using wooden blocks or metal brackets, creating deliberate gaps that American carpenters would deem wasteful and structurally unsound. When Samuel inquired why, Brennan described the European understanding that ground moisture traveled through masonry foundations more readily than most builders realized, especially in climates characterized by significant seasonal moisture variations. Armed with this newfound perspective, Samuel began examining deteriorated barns throughout the county with fresh eyes. His discoveries confirmed his worst suspicions. Every barn exhibiting premature sill rot displayed the same pattern. The darkest staining and most severe decay occurred precisely where the wood contacted the stone most directly. Barns with gaps or irregularities in their sill-to-foundation contact exhibited correspondingly less damage in those specific areas. The correlation was too consistent to dismiss. The solution Samuel devised challenged every established assumption about proper barn construction. Instead of placing the sills directly on the foundation, he would elevate them using wooden blocks cut from seasoned oak, creating a continuous 2-inch air gap between the sill and the stone. These blocks would be cut to precise dimensions, 4 inches wide, 6 inches long, and precisely 2 inches thick. He would space these blocks every 3 feet along the sill's length, providing adequate support while maintaining a consistent elevation. Through bolts would secure the sills to the foundation, passing through both the wooden blocks and into the stone below. This method necessitated additional materials and labor that standard construction avoided. However, Samuel calculated that the extra cost would prove insignificant compared to the expense of premature sill replacement. More importantly, the air gap would sever the capillary connection between the stone and the wood while still providing the structural bearing surface that engineers demanded. The wooden blocks would serve as sacrificial elements, easier and cheaper to replace than the massive sill logs if moisture damage eventually occurred. Samuel's neighbors reacted to his plans with predictable skepticism. The air gap violated fundamental assumptions about structural stability that had guided barn construction for generations. Critics argued that the elevated sills would create unwanted drafts, compromise the barn's thermal efficiency, and introduce unnecessary complexity into proven construction methods. Local builders warned that the wooden blocks would crush under the load, potentially causing catastrophic structural failure during the first heavy snow season. Despite this opposition, Samuel proceeded with construction in the spring of 1882, confident that only time would validate his theory. As his barn took shape, with its controversial air gap clearly visible, neighboring farmers gathered to witness what they considered either a stroke of genius or utter folly. The true verdict would not come in months, but in years, as moisture exacted its slow destruction on every barn in the county, except for one. Samuel's initial test of his theory manifested not as a dramatic failure, but in subtle signs that most farmers would overlook. Throughout the humid summer of 1883, he conducted daily observations of moisture behavior around foundations across the county, developing a systematic understanding of how water moved through different materials and construction joints. His method involved pressing his palm against foundation stones at dawn, when dew formation made moisture transfer most evident, then checking the same locations during the heat of midday, when evaporation reached its peak. The results revealed patterns that contradicted everything Wisconsin builders believed about dry stone foundations. Limestone blocks resting directly on soil consistently felt cool and slightly damp to the touch, even during extended dry periods. More significantly, Samuel discovered that this moisture traveled upward through the stone itself, reaching the top surface, where sill logs typically rested. He verified this by placing strips of birch bark between the stones and the soil for several weeks, then examining them for moisture damage. Every strip showed clear signs of water absorption, proving that ground moisture moved through stone more readily than anyone had suspected. Traditional building knowledge failed to account for the molecular behavior of water in porous materials. Samuel learned from James Crow Feather, a Ho-Chunk elder who worked seasonally on local farms, that indigenous builders had understood moisture transfer principles for generations before European settlement. Crow Feather explained how his people constructed elevated winter lodges using techniques specifically designed to prevent ground moisture from reaching wooden structural elements. The Ho-Chunk method employed natural materials like split cedar posts and carefully selected stones to create air spaces that interrupted moisture's upward movement through capillary action. This indigenous knowledge provided Samuel with a scientific framework that European-trained carpenters lacked. Crow Feather demonstrated how water molecules clung to each other and to porous surfaces, forming invisible chains that could transport moisture vertically through materials that appeared completely solid. When materials remained in direct contact, these molecular chains continued unbroken from the soil through the stone and into the wood. However, even a small air gap interrupted this process by breaking the physical connection that moisture required to travel between surfaces. Samuel tested this principle using materials readily available on his farm. He placed identical pieces of oak lumber in 3 different configurations, one piece directly on limestone, one elevated by wooden blocks, creating a 1-inch air gap, and one elevated by 3 inches. After 6 weeks of typical Wisconsin summer humidity, the results were unmistakable. The wood in direct contact with the stone showed visible darkening and felt noticeably damper than the elevated pieces. The 1-inch gap provided moderate protection, while the 3-inch elevation kept the wood completely dry despite identical exposure to ambient moisture conditions. These experiments convinced Samuel that his 2-inch air gap represented the minimum effective distance for breaking capillary moisture transfer under Wisconsin's specific climate conditions. Smaller gaps might provide some protection, but would not completely interrupt the molecular chains that transported water from the foundation to the sill. Larger gaps would offer additional protection, but would require more substantial support structures and introduce unnecessary complexity in construction. The seasonal test of Samuel's completed barn came during the exceptionally wet autumn of 1883, when continuous rains from September through November created ideal conditions for observing moisture-related structural problems. Traditional barns throughout the county exhibited accelerated darkening of their sill logs, with some structures developing the telltale black staining that indicated the onset of rot. Samuel's barn displayed no such symptoms, its sills remaining the same light oak color they had exhibited immediately after construction. More revealing was Samuel's discovery that temperature differences enhanced the effectiveness of his air gap system. During cool autumn mornings, when ground temperature remained warmer than air temperature, moisture-laden air rose from the soil and condensed on any available surfaces. In traditional barns, this condensation formed directly on the underside of the sill logs, where it could not evaporate quickly, initiating the slow process of wood deterioration. Samuel's air gap allowed this moisture-laden air to circulate freely, preventing condensation from accumulating on his sills, while providing natural ventilation that carried excess humidity away from the structure. The winter of 1883 to 84 provided the ultimate test of structural integrity. Wisconsin's climate demanded that barns withstand not only heavy snow loads, but also dramatic temperature swings that caused building materials to expand and contract repeatedly. Critics had predicted that Samuel's elevated sills would shift or settle under these stresses, potentially causing catastrophic structural failure when the barn's heavy timber frame required maximum support. Reality proved the opposite. Samuel's through-bolt system, combined with the wooden support blocks, actually provided superior stability compared to traditional direct contact construction. The bolts prevented horizontal movement while allowing slight vertical adjustment as materials responded to temperature changes. Traditional barns, with their sills locked rigidly against stone foundations, experienced stress concentrations at contact points that led to checking and splitting of structural timbers. Samuel documented this superior performance by measuring any movement in his barn's frame using simple but effective techniques. He drove small wooden stakes into the ground at precise distances from his barn's corners, then checked these measurements monthly throughout the winter using a surveyor's chain borrowed from the county office. Traditional barns in his area showed measurable settlement and slight movement as frost-penetrated foundations and structural timbers adjusted to temperature changes. Samuel's barn remained perfectly square and level throughout the entire winter, with no detectable movement in any direction. By the spring of 1884, the evidence had become impossible for local builders to ignore. Samuel's experimental barn had not only survived its first Wisconsin winter without damage, but had actually performed better than structures built using accepted methods. The 2-inch air gap had eliminated moisture-related deterioration, while the through-bolt system had provided superior structural stability. More importantly, these improvements had required no exotic materials or complex construction techniques that local carpenters could not easily replicate. Word of Samuel's success spread quietly through the farming community as neighbors observed his barn's superior condition compared to their own structures. However, widespread adoption of his methods would require more than a single season's proof. Wisconsin farmers needed to see long-term results before abandoning construction traditions that had served their families for generations. The real test would come not from one successful winter, but from years of consistent performance under the relentless stress of the upper Midwest's demanding climate. The structural demands of a Wisconsin dairy barn far exceeded anything most frontier carpenters had experienced in house construction. A typical barn carried loads that would crush a residential building: 40 tons of hay in the loft, 1,200 pounds per cow for a 30-head dairy herd, plus the dynamic forces created when animals moved and equipment operated. Traditional log construction relied on gravity and friction to hold these massive structures together, but Samuel had observed critical weaknesses in this approach that builders rarely acknowledged until catastrophic failure occurred. Standard barn construction employed wooden pegs, called trunnels, typically made from split oak and driven into holes drilled through overlapping timbers. These pegs worked adequately for the first few years after construction, when the wood remained tight and the joints stayed snug. However, Wisconsin's climate created seasonal expansion and contraction cycles that gradually loosened every joint in a traditionally built structure. Samuel had witnessed this process firsthand when helping neighbors repair barns that had developed dangerous sags and shifts after only 5 or 6 years of service. The problem intensified when structural movement combined with moisture-related wood deterioration. As sill logs softened from capillary moisture, they could no longer maintain tight bearing surfaces with the vertical posts and beams that transferred the barn's enormous weight to the foundation. Samuel discovered that traditional construction created what engineers would later recognize as a cascading failure system. Moisture weakened the base, which allowed structural movement, which opened gaps that admitted more moisture, which accelerated the deterioration process. Samuel's solution drew heavily on techniques that Heinrich Brennan, the German carpenter, had learned during his apprenticeship in Bavaria. European timber frame construction had evolved sophisticated methods for creating rigid connections between wooden structural members, particularly in regions where buildings needed to withstand centuries of use rather than the few decades that satisfied most American frontier construction. Brennan explained that German carpenters used forged iron bolts to create mechanical connections that remained tight regardless of wood movement or minor deterioration. The through-bolt system Samuel implemented represented a fundamental departure from traditional American barn construction philosophy. Instead of relying on wood-to-wood friction, he created positive mechanical connections using half-inch diameter iron bolts that passed completely through the sill logs and into threaded holes drilled in the foundation stones. Each bolt required precise positioning to avoid weakening the timber while providing maximum holding power. Samuel spaced the bolts every 4 feet along each sill, creating 8 connection points per side that distributed structural loads more evenly than traditional construction methods allowed. Manufacturing these bolts required cooperation with Jacob Steinmetz, the local blacksmith who had immigrated from Germany in 1878. Steinmetz possessed metalwork skills that American blacksmiths rarely needed, including the ability to forge threads directly onto iron rod and to create the specialized washers and nuts required for proper bolt installation. Each bolt cost Samuel nearly 50 cents to produce, representing a substantial investment compared to the wooden pegs that traditional construction used at no additional material cost. The installation process demanded precision that most barn raisings never achieved. Samuel first marked the exact position of each bolt while the sills remained on the ground, using a chalk line to ensure perfect alignment along the timber's length. He then drilled the bolt holes using a 2-inch auger, creating clean openings that would not weaken the wood grain. Most critically, he drilled corresponding holes in the foundation stones using star drills and careful hammer work, creating threaded recesses that would accept the bolts securely. The mechanical advantage of this system became apparent during the barn's second winter, when neighboring structures began showing the telltale signs of structural settlement. Traditional barns developed visible sags in their roof lines as wooden joints loosened and structural members shifted under load. Samuel's barn maintained perfect alignment because the through bolts prevented any horizontal or vertical movement of the sill logs relative to the foundation. Even when temperature changes caused the wooden structural members to expand and contract, the mechanical connections held everything in proper position. Samuel verified this superior performance using measurement techniques that revealed problems invisible to casual observation. He stretched string lines between wooden stakes driven into the ground at precise distances from his barn's corners, creating reference points that allowed him to detect movement as small as a 1/4 inch. Monthly measurements throughout the winter of 1884 to 85 showed zero detectable movement in his barn structure, while similar measurements of neighboring barns revealed settlements of 2 to 4 inches as their foundations shifted and their structural joints loosened. The load distribution characteristics of Samuel's system provided additional advantages that became apparent under extreme conditions. During a severe ice storm in February of 1885, accumulating ice added an estimated 15 tons of additional load to every barn roof in the county. Traditional structures responded to this stress by developing new cracks and separations at their weakest joints, typically where sill logs met corner posts or where plates connected to vertical supports. Samuel's through-bolt system transferred these loads directly into the stone foundation, bypassing the wood-to-wood connections that failed in other barns. More importantly, the rigid connection between sill and foundation created what engineers would recognize as a moment connection, capable of resisting both vertical loads and overturning forces. Traditional barns relied entirely on their own weight to resist wind loads and other lateral forces, making them vulnerable to structural failure during severe storms. Samuel's bolted connection allowed his barn to resist these forces mechanically, providing a safety margin that traditional construction could not match. The economic implications of this improved structural performance became clear as Samuel's neighbors faced costly repairs that his barn avoided entirely. By 1886, 3 barns within 2 miles of Samuel's farm required major structural work to correct settling and shifting problems. These repairs typically involved jacking up the entire structure, replacing damaged sill logs, and rebuilding failed joints at costs ranging from $150 to $300 per barn. Samuel's initial investment of approximately $40 in through bolts and specialized labor had eliminated these ongoing maintenance costs completely. The integration of through-bolt structural connections with the air gap moisture control system created synergistic effects that neither technique could achieve independently. The mechanical stability provided by the bolts ensured that the critical 2-inch air gap remained consistent even as the building's structural members responded to seasonal changes. Simultaneously, the moisture protection provided by the air gap prevented the wood deterioration that would eventually compromise even the best mechanical connections. Samuel began documenting these advantages systematically, keeping detailed records of his barn's performance compared to traditional structures throughout the county. His measurements and observations would eventually provide the evidence needed to convince skeptical neighbors that his unconventional methods delivered superior results. However, the ultimate test of structural integrity would require not just 1 or 2 seasons of superior performance, but decades of consistent reliability under the demanding conditions that Wisconsin's climate imposed on every agricultural building. The winter of 1887 to 88 delivered the most punishing test of barn construction that Wisconsin had experienced in a generation. January temperatures plummeted to 28 degrees below zero and remained there for 6 consecutive days, creating thermal stress conditions that revealed hidden weaknesses in every agricultural structure across the county. The extreme cold was followed immediately by an unusual warming period that brought temperatures above freezing for 3 days in early February, then plunged back to sub-zero conditions, creating expansion and contraction cycles that most wooden structures could not withstand without damage. Samuel discovered that his air gap system provided unexpected thermal advantages that conventional construction completely lacked. The 2-inch space beneath his sills created an insulating air pocket that moderated temperature changes in the structural wood, preventing the rapid expansion and contraction that split timbers in traditional barns. More significantly, the gap allowed air circulation that carried away moisture vapor from livestock and stored feed, preventing the humidity buildup that caused condensation and subsequent freezing damage in tightly sealed structures. Traditional barn construction assumed that eliminating air spaces would improve thermal efficiency. But Samuel's observations proved this assumption catastrophically wrong. Neighboring barns, with their sills sealed directly against stone foundations, trapped warm, moist air that rose from animal body heat and hay respiration. When this humid air contacted the cold stone foundations, it condensed and often froze, creating ice accumulations that expanded and cracked both stone and wood. Samuel's barn avoided this problem entirely because the air gap provided a circulation path that carried excess moisture away before it could condense and freeze. The thermal dynamics of Samuel's system revealed principles that would not be formally understood by building scientists for another 50 years. During the day, solar radiation warmed the barn's roof and upper walls, creating convective air currents that drew fresh air through the foundation gap and expelled stale, humid air through the upper reaches of the structure. At night, when temperatures dropped rapidly, the air circulation continued, but at a slower rate, preventing the stagnant conditions that led to condensation problems in sealed buildings. This natural ventilation system required no mechanical devices and operated automatically in response to temperature differences. The severe test came during the February thaw, when daytime temperatures reached 42 degrees while nighttime lows dropped to 14 below zero. These extreme temperature swings created thermal shock conditions that caused traditional barn timbers to check and split as their outer surfaces expanded and contracted while their cores remained at different temperatures. Samuel monitored this phenomenon by examining the structural timbers in his own barn and comparing them to similar members in conventional structures throughout the area. Samuel's through-bolt system demonstrated additional advantages under these thermal stress conditions that pure moisture control could not provide. The mechanical connections allowed his structural timbers to move slightly as they responded to temperature changes, but prevented the accumulation of movement that led to permanent deformation in traditional buildings. Each bolt acted as a fixed reference point that maintained proper alignment while allowing the natural expansion and contraction that occurred in all wooden construction. Traditional barns lacked these mechanical controls and often developed permanent twists and distortions as their structural members responded to repeated thermal cycles. The integration of thermal management with moisture control created performance characteristics that exceeded the sum of either system operating independently. The air circulation provided by the foundation gap helped moderate temperature swings in the structural wood, while the through-bolt connections prevented thermal movement from accumulating into structural distortion. Most importantly, the combination eliminated the freeze-thaw cycles in wood-to-stone contact points that destroyed traditional barn foundations throughout Wisconsin's climate zones. Samuel documented the superior performance of his system during the brutal spring of 1888, when alternating periods of heavy rain and hard freezes created the most challenging conditions for barn foundations that local farmers had ever experienced. Here's the translation and rewrite, aiming for clarity, flow, and a touch of expansion where helpful. The ground went through relentless cycles, becoming saturated with water, then freezing solid, only to thaw and become waterlogged again. This pattern repeated weekly from March until early May, creating maximum stress on barn foundation systems. The saturated soil expanded significantly when frozen, generating uplift forces that could crack stone foundations and even shift entire structures. Traditional barns suffered considerably during this period because their rigid connections between the sill and the foundation couldn't accommodate the ground movement caused by these freeze-thaw cycles. Samuel noticed foundation stones shifting by several inches as the frozen soil expanded beneath them, leading to permanent misalignment in barn structures that had stood straight for decades. His own barn experienced the same harsh soil conditions, but showed no signs of distress. This was because his through-bolt system allowed for slight foundation movement while maintaining the overall structural alignment. Furthermore, the air gap effectively prevented frost from penetrating deeply enough to affect the wooden structural members. The economic impact of these differences in performance became strikingly clear as Samuel's neighbors faced significant repair costs that his innovative system had completely avoided. Thomas Mackenzie, who ran the nearest dairy farm, spent $120 replacing cracked foundation stones and realigning his barn's structural frame after the spring thaw of 1888. Heinrich Schultz, whose farm was just a mile from Samuel's, discovered extensive cracking in his sill logs due to the repeated freeze-thaw cycles and faced repair bills exceeding $200 to prevent structural failure. Samuel's meticulous record-keeping revealed that his barn had endured identical weather conditions without suffering any measurable damage or requiring repairs beyond routine maintenance. The initial investment in air gap construction and through-bolt connections had eliminated ongoing repair costs, while also providing superior structural performance under the most demanding conditions that Wisconsin winters could deliver. Crucially, the system had proven its effectiveness without requiring specialized maintenance skills or materials that local farmers couldn't easily obtain. By the autumn of 1888, Samuel's methods had withstood 6 years of Wisconsin weather, including 2 exceptionally severe winter-spring cycles that had damaged or destroyed dozens of conventional barns throughout the county. His detailed documentation consistently demonstrated superior performance in moisture control, structural stability, and thermal management compared to traditional construction methods. The evidence had become impossible for practical farmers to ignore. However, widespread adoption would require overcoming decades of ingrained building traditions and the natural conservatism of agricultural communities that simply couldn't afford costly construction failures. The true test of Samuel's innovation would come not just from surviving individual weather events, but from decades of consistent performance that proved his methods could outlast the traditional construction they challenged. Only long-term reliability could truly convince Wisconsin's pragmatic farmers to abandon their proven techniques for methods that seemed to violate fundamental assumptions about proper barn construction. The drought of 1891 shattered all previous weather records across Wisconsin, with a mere 11 inches of rainfall recorded between May and September, compared to the normal 32 inches for the same period. When the rains finally returned in late September, they arrived with unprecedented intensity, delivering 7 inches in just 4 days, followed by persistent drizzle that continued into November. This extreme wet-dry cycle created the ultimate test for foundation systems because the drought had caused soil shrinkage, opening deep cracks around every barn foundation and providing pathways for the subsequent deluge to penetrate areas that normally remain dry. Samuel had developed systematic methods for monitoring foundation performance, revealing the full scope of problems that conventional barns experienced during this crisis. Using a simple but effective technique he'd learned from railroad surveyors, he drove wooden stakes at precise, measured distances from the foundation corners of multiple barns throughout the area. He then used a surveyor's chain to detect any movement, even as small as 1/4 of an inch. His monthly measurements throughout the 1891 crisis documented foundation settlements and shifts that barn owners never suspected until structural damage became visibly apparent. The results proved devastating for traditional construction. Every conventionally built barn in Samuel's monitoring network showed measurable foundation movement during the drought flood cycle, with settlements ranging from 1 to 4 inches at various points along their perimeters. Critically, these foundations never fully returned to their original positions when soil conditions stabilized, leading to permanent structural distortions that compromised their load-bearing capacity and accelerated overall deterioration. Samuel's barn, in contrast, registered zero detectable movement throughout the entire crisis period, demonstrating that his integrated system could withstand extreme soil conditions that utterly destroyed conventional foundations. The moisture management advantages of Samuel's system became even more apparent during the humid summer of 1892. Persistent high humidity, combined with temperatures consistently above 85 degrees Fahrenheit, created ideal conditions for wood rot in any structure that trapped moisture. Traditional barns throughout Wisconsin experienced an explosive growth of fungal decay during this period because their sealed sill-to-foundation connections prevented adequate air circulation, which would have removed excess humidity from the structural wood. Samuel discovered that his foundation air gap created a natural chimney effect that effectively drew humid air away from the wooden structural members, even during the most challenging atmospheric conditions. Samuel's documentation methods had evolved into a comprehensive monitoring system, providing quantitative evidence of his barn's superior performance. He maintained detailed logbooks, recording temperature and humidity measurements taken at 3 locations within his barn and at comparable locations in neighboring structures. His data showed that humidity levels in traditional barns often exceeded 90% during summer evenings, while his barn rarely exceeded 70% under identical conditions. This 20% difference in relative humidity represented the critical margin between rapid wood decay and long-term structural preservation. The economic advantages of Samuel's system reached a tipping point during the financial panic of 1893. Falling agricultural prices made expensive barn repairs simply unaffordable for most farmers. Harold Peterson, whose barn required complete sill replacement at a cost of $350, faced the grim choice between mortgaging his farm or allowing his barn to collapse. Meanwhile, Samuel's barn required no repairs beyond routine maintenance, which cost less than $10 per year for paint and minor hardware replacement. This dramatic cost differential finally convinced practical farmers that Samuel's initially more expensive construction methods delivered superior long-term value. The first successful adoption of Samuel's techniques occurred in 1894 when Robert Olsen, a Norwegian immigrant farmer, incorporated both the air gap and through-bolt systems into his new barn construction. Olsen cleverly modified Samuel's original design by using locally quarried granite blocks instead of limestone for his foundation, creating a more durable base that could better withstand the mechanical stresses created by the through-bolt connections. His adaptation proved that Samuel's principles could be successfully applied using different materials and construction techniques while maintaining the essential performance characteristics. Olsen's successful implementation encouraged other farmers to experiment with variations of Samuel's methods. Eric Larson developed a hybrid approach that used traditional wooden block foundations elevated 6 inches above ground level, combined with Samuel's through-bolt attachment system. This modification reduced construction costs while providing most of the moisture protection benefits of the air gap design. Anders Christensen created another variation, using steel brackets manufactured by the local blacksmith to support sills above stone foundations, eliminating the wooden support blocks that required periodic replacement. The spread of these techniques accelerated significantly when Magnus Thompson, a respected barn builder who served farmers across 3 counties, began incorporating Samuel's methods into his standard construction practices. Thompson had observed the superior performance of air gap barns during his routine maintenance visits and recognized that adopting these methods would reduce his long-term repair obligations while also enhancing his reputation for quality construction. By 1896, Thompson estimated that 60% of his new barn construction incorporated some variation of Samuel's moisture control and structural attachment innovations. Samuel's influence extended beyond individual farm construction when his methods attracted the attention of agricultural extension agents working for the Wisconsin State University system. Professor William Sterling, who directed the university's agricultural engineering program, visited Samuel's farm in 1897 to document construction techniques that had proven successful under Wisconsin conditions. Sterling's subsequent publications in agricultural journals provided the first systematic technical analysis of air gap foundation systems, establishing scientific credibility for methods that had previously been dismissed as unconventional. The validation of Samuel's techniques appeared most clearly in the agricultural building guides published after 1900, which routinely included recommendations for elevated sill construction and mechanical attachment systems. The Wisconsin Farmer's Manual of 1903 devoted 4 pages to foundation moisture control methods, explicitly crediting innovations developed by practical farmers who had challenged conventional construction wisdom. Similar recommendations appeared in building guides published throughout the Upper Midwest, indicating that Samuel's locally developed solutions had achieved regional acceptance among professional builders. By 1910, Samuel's original barn had operated successfully for 28 years without requiring any major structural repairs. While most conventionally built barns in the area had undergone at least one expensive foundation renovation, his systematic documentation proved that initial construction investments in moisture control and structural stability delivered measurable economic returns through reduced maintenance costs and an extended building lifespan. More importantly, his methods had evolved from experimental techniques into accepted regional building practices that protected thousands of agricultural structures across Wisconsin's demanding climate. The legacy of Samuel's innovation extended far beyond his individual success, demonstrating how practical observation and systematic experimentation could improve upon established technical traditions. His willingness to challenge conventional wisdom, combined with careful measurement of results, created knowledge that benefited the entire agricultural community while establishing principles that would guide barn construction for generations to come. The techniques he developed through patient observation of moisture behavior and structural performance had transformed from local curiosities into standard practices that defined superior agricultural construction throughout the upper Midwest.
Best.